Your smartphone will, my sense is in the future, your smartphone will measure even more about you than it already is. So basically we have measurement devices that are around us everywhere. A lot of you have laptops. If my talk is boring, some of you might decide to like go look at other websites. When you click on other websites, they're collecting data about you there. So there's like link information. If you've ever tweeted, used Facebook, posted, that's big data Facebook is collecting. That's big data that Twitter's collecting. So basically, we sort of are just measuring more and more things in just various different ways. And I'll get to that point later. And again, you know, when they talk about, so really one of the big things people want to look at is in this bullet point, basically looking at correlations for spotting things like business trends, so business companies, and again, so I'll also throw some jargon along the way. So one jargon for big data, if you want to sound like you know about what big data, are FANG companies. Does anybody know what FANG companies are? F-A-N-G. So the F is Facebook, the A is Amazon, the N is Netflix, the G is Google. So FANG companies. So again, these are basically again people that I think you would are definitely doing a lot of big data work. So obviously those companies we're going to want to spot business trends. Probably from our point of view as an academic health center, we're sort of thinking more about things like quality of research, disease prevention. But again, other disciplines as well, like law, criminology, they're thinking about how to combat crime. And then probably one we're all very familiar with, if you have things like Google Maps or Waze on your phone, is determining real-time traffic conditions. Okay, so in terms of what gets used, as Ali mentioned at the beginning of the talk, there's a lot of techniques that are used here. And again, being the chair of the Department of Biostatistics on this campus, basically in informatics, things like statistics, information science, you see that a lot. So there's a lot of methods to be learned. And the other reality is that we could probably all spend the rest of our lives trying to learn all these methods, right? So one big thing about big data is this is not ever going to be something that we all do by ourselves. This has to, for sure, by definition, has to be a collaborative, team-oriented activity. Okay, so that was all the definition stuff. Again, it's from Wikipedia. There's also a criticism of it. So, and again, this is one that, again, as being a statistician, we sort of are familiar with as well. Also, I'll point you to the last sentence, or a couple last sentences, which is, so at our big meeting in statistics, it's called the Joint Statistical Meetings. One year we had Nate Silver, who does the 538.com website, for those of you who don't know, which right now is doing all the polling prediction, right? So again, with the polling prediction, what he's doing is he's importing all the data sets from various surveys, using that to come up with a model for predicting who's more likely to win, Hillary Clinton or Donald Trump, for the presidency. So he had this quote at that meeting, towards the end here. I think data scientist is a sexed up term for a statistician. Probably the first time you'll ever hear statistician and sexy in the same sentence, but we'll leave that alone. Statistics is a branch of science. Data scientist is slightly redundant in some ways, and people shouldn't break the term statistician. So what I'll say today is basically, when we talk about data, big data science, what I'll talk about today is life cycle process that Beth alluded to. And what I'll say is in what I described, there's a role for statistics. But there's actually a role for other things as well. And the other thing I'll say too is there's probably, there are things that are statistical that as a discipline we haven't been as good about promoting. So we'll get to those slides later. I promise you there'll be way more pictures going forward. So here's some other references. So again, one thing you might hear about is this number that like in, I forget, 15 or 20 years, we're gonna have 108,000 jobs in data science, and we're basically, and we're basically not training people at that rate. That comes from this McKinsey report, which is the first link. The other ones are basically various statisticians sort of thinking about how stats plays a role in data science. Okay, so getting some pictures. So just to show you a little bit of more visualization of this stuff. So one way, again, that big data get generated, and I'll have to talk about it more later, is people searching on Google. So every time you search something on Google, that's a data point, right? And there are probably trillions of searches being done every day. So that, again, is a different big data. So this is just an example of a few terms. So data science, big data, machine learning. So big data is in blue, red. Data science is in blue, and then machine learning is sort of the yellowish one. And what you basically see is around early 2011, there was a big spike in the big data searches, right? So basically, the term big data really, I think I would say, took off sort of in the early 2011. And the other one's sort of going increasing, but definitely not the way big data is. Okay, so here's more. That looked impressive, but now I want to add in statistics. So you basically see how statistics sort of dwarfs the other ones. So this actually will point out to one big problem with what I just said, though, which is it looks like people are querying statistics more, but as you can imagine, statistics actually have a lot of meanings, right? So this is one of the big things in big data. So statistics is a word. Figuring out what people really mean when they're searching for statistics, that's actually a informatics task that they call disambiguation. So in a sense, really, statistics could be, they care so much about the discipline of statistics, they just want to know statistics on something. They're big baseball fans, they want to know the statistics of, who's the guy, Nolan Coronado, the Rockies guy? Yeah, so yeah. So there can be, so statistics can, that word can mean a lot of different things. And figuring out what exactly people mean, that is a informatics challenge. So yes, I think that's probably the reason why this is dwarfing. I'm going to not say that this is interest in our profession, which also sadly looks like it's going down over time. But anyhow, okay. So thinking about big data, there are lots of characteristics of it. So this, I'm going to show you two pictures from IBM. So there's a lot going on in these pictures, but I think these actually speak to the features about it. So I'm going to go starting from the upper left. So when people think about big data, they think about the volume, right? And like I said, you're going to learn all kinds of fun prefixes on bytes. So let's see. So one example up here is in 2020, there'll be 40 zettabytes of data being created. So I've never even heard of zetta. Turns out zetta is a trillion giga. Okay, so again, when you get to prefixes we're not even familiar with, I mean, really the impression you're taking is a lot. And again, basically, like I said, I really think of cell phones as being one of the main sources of this data generation and data measurement. And right now, 6 billion people in the world have cell phones. And yeah, so again, 2.3 trillion gigabytes of data being generated every day. And then, and now, I mean, think about flash drives and hard drives. So now you can buy routinely hard drives that have like, external hard drives that have like terabytes of data, right? So basically, this is sort of, so yeah, so it says that most companies in the US have at least 100 terabytes of data being stored. And I think that's also true for our campus as well. So the volume is something I think people think about with big data, but there are actually 3 other, I think, aspects that are sort of, important. One is this, which is variety. And like I said, data really comes in a lot more heterogeneous formats than statisticians are used to. So again, a statistician, just to pick up my profession, we conceptualize a matrix with numbers in the matrix, right? How you get to those numbers in the matrix now has actually become a lot more complicated. So here's some pictures. So obviously, if any of you guys wear things like smart watches or Fitbits and things like that, you're wearing a wireless monitor, which collects data on you. So they predicted in 2014, 420 million people have wearable watches or health monitors. Some of you might go to the website YouTube, which has video. You can think of video as being another data source, right? As I mentioned, Facebook, Twitter. Facebook, the content on Facebook is a source of data. You can think of it this way: you might want to make friends on Facebook or like things on Facebook. Whenever you make a friend request, when you click like on a link, that's data that's being collected. And basically, the other thing I'll get to is Facebook as a company, right? So they have people there that are using machine learning in ways that we don't even know about. But basically, based on what you like, they then figure out, oh, what content should we prioritize to show you in the future, right? So, and then there's also Twitter. The other thing that's happening, which sort of is not talked about here, is basically there's variety, but there's also crosstalk across websites. So now, let's say you go to Amazon and you look for a pair of new glasses on Amazon. you might end up seeing in your Facebook post or Facebook webpage, you recommended those glasses from Amazon. And you're wondering, how did that happen? Well, it happened because basically of your web activity and the fact that sort of developing linkages between what URLs you're looking at on Amazon versus what your Facebook. So yeah, so there's a lot of crosstalk. And again, one of the issues I'll get to, and again, this is actually more relevant, I think, for us, is at a health center, given all that much crosstalk, one of the things that can actually happen is that it'll become very easy to spot you based on your web activity, based on your searches. And again, one of the things we hold very utmost and near here in a medical setting, which is really important, and for ethical reasons, obviously, as well as more, is basically patient privacy, right? So I think thinking about how you maintain privacy with this kind of data lying around is actually a really big challenge. So I don't have solutions, but I think something just to be well aware of with big data. Okay, so bottom left is another thing we sort of don't think a whole lot about, but actually a lot of data are being collected, but it's also being collected pretty quickly. So again, it's sort of one thing I think, so when people give talks on big data, I think it's one aspect that tends to get ignored, which is a lot of the data we collect is being collected dynamically, okay? So one of the things you're going to want to do is that, again, as a statistician, you have a model, you fit it to the data. If you collect new data, you want to update your model, right? It's a very basic sort of stats principle. But now we're collecting lots of data that's coming to us really, really quickly. So really what this really means, again, this is more of a computational task, I think, really is basically you're getting lots of data, you want to update models. How do you do that in a way that's sort of computationally feasible? So yeah. And again, the examples they give here. So New York Stock Exchange, right? They have stock, they have stock prices go up, they go down, and that's being there's 1 billion terabytes of traded information, which is being generated and monitored during each trading session. So again, there's sort of a dynamic aspect to big data, and again, most of what I talk about today will not be, definitely the second half talk will not necessarily be dynamic, but thinking about how you develop computational algorithms that can handle dynamic updates is actually a big open topic, I think. The last one, which is actually probably the more disconcerting one, is actually the quality of the data or the veracity. And so let's see, this is from a poll where they basically where they surveyed business leaders, and basically a third of them said they don't trust information. 30% said they weren't sure how much of the data was, or they weren't sure how much of the data was inaccurate. And then the other thing too is there's actually a data quality issue, right? So the reality is, and this again sort of I'll get to the second half of the talk, we make decisions based on this kind of on these data sources, right? And then the question becomes, if the data aren't good, we're making less than optimal decisions. So there's been people in health services and health economics or economists try to figure out how much are we sort of costing the U.S. economy by making poor decisions. And you can estimate these things based on different scenarios and models, and one estimate says $3 trillion a year. Okay, so those are 4 V's of big data. This comes from IBM at that URL up there. They actually updated the poster, so there actually might be a 5th one. So it's the same poster. I'm not going to go through it, but there's a 5th V. Can anyone guess what the 5th V might be?
Value.
Yes, value. So the idea is by having, and again, it's sort of the flip of what I just said, by having big data, by processing accurately, by making optimal decisions, we actually save money, or we achieve value. So, so that's right. And again, one thing I sort of want to point out is to think about value or to conceptualize it, you need to have a comparison strategy, right? You need to think, what would I be doing? How would I be operating in the absence of the big data and the processing? What would I do differently once I have the big data and once I analyze and process and interpret it correctly? And that difference, which hopefully is, if you think about money, is savings, that's the value. Okay, so I'm going to come back to this framework later, but again, this sort of is a life cycle process that Beth alluded to in her introduction. So there's a lot going on with big data, and these are super clunky graphics, so I apologize, but really the words are sort of the key thing here. So the data resides somewhere, and then basically big data sort of is thinking about how you take the data down here and eventually come to knowledge, right? So there are all these steps that get done. So here's actually a big step. Based on the data, I need to somehow sample or select the data that I need. So the question then becomes, how do I do that? And again, to me, the selection step is actually a super crucial step. And again, I think one thing I would tell you is, I think statisticians, we like doing stuff later in the process. I spend a lot of time thinking about it. But I think in terms of choices, actually, these choices early on are the ones that actually have the bigger impact, ultimately, on your final answer. So how you select data, you get the data, and then you might have some sort of time frame or time period you want to be sampling within. Once you get that data, how do you then process the data? And again, this pre-processing is something that is going to be really important. But again, typically, I think we don't, at least in our curriculum, we don't spend a whole lot of time talking about the pre-processing step as being important. I think this is actually one of the big distinctions between data science and thinking about statistics. Is basically they spend a lot of time thinking about this step, how you pre-process things. And I think later today you'll have talks on how to think about standardizing and normalizing variables in the big data setting. So let's say you do, so basically these pre-processing and transforming are, data, I'll call them, if you want to sound like a real up-to-date data scientist, they call those data munging and data wrangling steps. So these pre-processing transformation, and then you sort of get to the data. So this data, the transformed data, is what you end up working with. And then once you do that, you use a lot of what big data involves, basically finding patterns, which we'll spend a lot of time talking about today. And this idea of finding patterns falls under this general title of machine learning or data mining algorithms, which I'll talk about later. But the basic idea of data mining is to then sort of find patterns. And then once you find those patterns, you then interpret, evaluate, and ostensibly get to knowledge. So I'll talk more about this later as well. Things to note here, though, as a statistician, like I said, how you collect your data or where you collect it from, or actually maintaining data quality, sort of down here is an important thing. Again, we use this phrase in our field, garbage in, garbage out. So if you're collecting data and you're not sort of having quality control checks and whatnot, this isn't going to be very high quality, which is going to make everything else not be very high quality. And again, this is for big data. This could be very heterogeneous. This could come from multiple studies, multiple hospitals, multiple providers. So there are all those kinds of issues. So again, I think a big issue is different studies might collect information different ways. So you want to have sort of you want to be aware of that. B, you want to figure out is there a way of standardizing across studies? So this idea of standardization is actually a big one among informaticians that work with big data. What else? So the idea here too is, as a statistician, I can tell you, if you have a big enough data set, you'll find a pattern, right? I can put sort of noise in this and I can come up with a pattern. So really trying to figure, so there's sort of two issues here. And again, if you're taking stack course, you're probably familiar with this. There are patterns that might be statistically significant. There might be patterns that are non-statistically significant. Trying to combine that with the idea of it being a clinically meaningful pattern versus a non-clinically meaningful pattern is, that challenge does not go away with big data. And in fact, I would tell you it gets actually it gets harder because there's probably more complex patterns that you're sort of trying to figure out. The last thing I sort of want to say too is, for now, is this idea of knowledge. Ostensibly, again, you're sort of so again, a lot of our campus thinks a lot with discovery, finding new genes that affect cancer, finding new molecules that could be potentially used for treating, preventing disease, detecting disease, treating disease. But when you think about knowledge, really this pipeline, this knowledge is helpful if it leads to a change in a decision, right? And again, I think thinking about changes in decision and whatnot really falls into the domain of again, people that work in causal modeling. Because in causal modeling, I'll talk about this later, you think about these counterfactual outcomes where you imagine what your response would be under different scenarios. And then hopefully this knowledge that they get through the big data will sort of help you in figuring out what sort of the optimal scenario for your patient, for your subject, for whoever you're working with. So I think the causal modeling approach has a lot to offer here. Okay, so again, some things that I've said all this already. So I showed you a really not great graphic of big data pipeline basically for it. But actually, again, in big data, in the data mining, data knowledge world, they talk a lot about use cases. So I think of use cases as the actual scientific problem or context you're looking at. And I think actually there, you have context knowledge that matters. And, and as a statistician, I'd argue you probably would want to be thinking about you trying to use that in some way. Again, really big data you can't process using sort of your standard tools on desktops or laptops. And again, I alluded to this before with that thing about velocity. There's actually a dynamic aspect to big data that potentially can make things more computationally intense. Again, I think a lot of what we'll get talked about today will basically be things that are not dynamic; they're static. But yeah, I think sort of fully realizing big data, its potential. I think a lot of it is this idea of like you build a model, you get new data, you update the model in real time. Fourth one, again, this is an opinion. Maybe a self-serving one because this is what I work on, but a lot of the questions we want to use big data to solve are actually causal in nature. And then as a statistician, a lot of what I think about is when you generate data, you think about the data generating process, where are sources for variability, where are sources for bias. So really, I think in big data land, identifying those sources of variation and bias are key. And again, this is something that the discipline of biostatistics, discipline of epidemiology has thought about for a long time. I think what's going to happen, and I'll show you hopefully through a case study, is that in fact the number of places where things can go wrong is going to kind of exponentiate. That's my prediction, in ways we haven't sort of imagined, just because of the availability of sort of new technology on platforms. Okay, so I want to go through sort of one case study, and this is a thing out of Google. So you might have heard about this a few years ago. So it's called the Google Flu Trends Model, and the idea is the following. What Google wanted to do was the following. They wanted to take, so users, again, when they get sick, they might search about it on Google, okay? So Google wanted to sort of monitor what people are searching on. And again, when people do these searches, they're doing it from a computer. The computer has an IP address. In principle, you can then take the IP address and then use sort of geocoding techniques to sort of spatially locate where the computer server is. And so the idea would then be, if I see, so again, yeah, so my example here, if users in Nebraska are querying flu and related terms, that becomes a data point analysis. So then the question becomes, are people in Nebraska searching for flu more often than you'd expect by chance? Okay? And again, expect by chance is can be kind of debated as how you define that, but let's say they are. They wanted to then sort of say, is there a flu outbreak in Nebraska? And obviously, I'm using Nebraska, which is a really big state. You can localize that a lot more to thinking about stuff at the county level, city level. You can sort of pick your geographic unit of interest here. But basically, the idea was, based on search terms, could I then use logistic regression to predict the likelihood of flu-related illness based on queries on search terms in that area? So the big data aspect is, like I said, people are searching Google all the time. They have lots of data points to do this with. So basically, they are crunching trillions of time series points in a dynamic manner to build this predictive model. Okay. So that's sort of the backdrop. This paper came out in 2014 in Nature. So here's one of the things they show. So the black is sort of the observed data. The red is what's predicted from the model. It's really good. So they had sort of, accuracy kinds of, they had measures of predictive accuracy, where like 0 is bad, 100 is good. They were in the high 90s. So they were saying this is a really good thing. So anyhow, and also want to keep track of the things on the bottom here, the years. So the years start from roughly 2004, go up to about 2008. Okay, so issues came up after this paper got published. First, one I'll talk about, I'm not sure how much you're going to talk about today, but like one is actually an ethical issue, and I alluded to this earlier. So basically, is the privacy of individuals maintained with big data? And again, so I'm giving you a bit of a letter, excerpt from a letter from the Electronic Privacy Center to the CEO of Google, Eric Schmidt. And again, probably, yeah. It's a long letter, but I accepted what that was with all the paragraphs here. So yeah, so very nice opening paragraph, but basically sort of the middle and second and third, so key ones here. At the same time, there's an obvious privacy concern. Search for histories reveal personal information, and medical inquiries are pretty sensitive. So the search for flu symptoms could easily be a search for AIDS symptoms or Ritalin or Paxil. So if a person is HIV infected, basically, you can imagine this would be a way that they could get their status like disclosed through Google, which is really kind of scary, right? So again, those search queries can be super sensitive and basically reveal the person effectively. And again, this is Google. This is just Google data. If I were to then take Google data and start to overlay with other data sets, right? Let's say this person who's looking for AIDS symptoms then starts to like look up, go to things like WebMD or something and look up HIV or something. I mean, if you start to overlay the WebMD with the Google, and then maybe also this person also then looks at Facebook groups for HIV positive communities, that person you probably get identified super quickly. So again, this is called, so basically this is a data privacy issue. And again, in that community, they basically talk about, so I'm blanking on the term now. So it's basically sort of an information attack to basically disclose the individual. So the risk of patient disclosure can go up really quickly with big data. So that's all I'll say about it today. So again, the aggregate, the data useful trends. But again, here's the main thing. If disclosed, which I was saying, linked to a particular user, if you identify the person, you can imagine lots of adverse consequences. So I think partly in response to this, they actually stopped sort of really updating things, because I think there was a big worry about the maintaining privacy. And again, maintaining privacy is something you sort of hear over and over again about people who work with big data. And I describe it as basically sort of an ethical kind of issue that I actually still don't think is really resolved yet. Here's the other one, which I'm sort of a little bit more familiar with, which is more quantitative and statistical in nature. So this data was looked at and sort of reanalyzed by a group out of Carnegie Mellon and Harvard. And they have a couple points here. So basically so one point they have, which is, again, one I think a lot of us would agree with, potentially, so Google Flu is just using their predicted model. They actually then sort of looked at, so the CDC also has a model for doing this. They basically fit sort of a lag time series model to do predictions. And they sort of compare the Google Flu with the CDC, the lag CDC model. They also look at combined information. So one of the things they found in their data set was when sort of done properly, combined information was better than just the Google Flu model, which makes a lot of sense, right? If you can bring in relevant information in a way that's sort of, consistent and compatible with the model you have, you might do better prediction-wise. But the other thing I want to sort of point out are a couple things out here. So basically, if you start looking at the Google Flu model, it starts to do a lot worse out here. So basically, they point out here that Google estimates are more than double CDC estimates. So there's actually a lot of variability out here. But the thing I want to point you down to is down here. So basically, if you remember, what I showed you was 2004 to 2009 for the Nature paper. This is now looking at 2009 onwards. And you sort of see this happening. So you look at the Google Flu model and lag CDC, they look fairly concordant. But then around early July 20th, 2011, the orange line goes consistently above the rest, okay? So Google starts estimating high relative to CDC 100 out of 108 weeks, okay? So yeah, the orange line is above the other lines. So what happened? So it turned out, not without really people knowing, they actually expanded the scope of their search terms related to flu. Okay. So in their model, they were sort of counting certain terms before July 2011. After July 2011, they actually expanded what terms they were counting. Okay. So basically, the terms they might have added in might have started to bias things, right? So basically, I could call this like a search term bias. Okay. So that's sort of one issue that came up. And again, they sort of modified their algorithm, which is the fragment predictive model. But here's the third one, which is kind of kicker, right? Which is that Google's a private company. We use them all the time, but they're still a .com. They're not a .edu. They're not a .gov. because they're a private company, there is no possibility of getting a transparent and reproducible algorithm from them for generating results, right? It's in their interest as a company, because ostensibly this is one of the things that gives them a market advantage for people who want to use them, and it's sort of what's positive for their business. There's no incentive for them at all, right, to give anyone off the street sort of a copy of their model. So this is the other thing I'll sort of bring up as well. With big data, you're fitting really complex models. And if you don't have methods, and I've bolded reproducible here, if you don't have methods for being able to reproduce things, that's going to make, that's just going to lead to breakdowns in many ways. And again, I think later you guys have talks by people thinking about reproducible issues with big data. Okay, so key points of the laser wall paper. One was thinking about this idea of being able to reproduce and replicate things with big data. The other thing that they sort of said is basically there's a cost benefit that underlies big data analysis as well. So basically what they sort of say, their quote in the paper is basically the CDC model got you sort of 90% of the way there. So is it really in Google's best interest to try and so there's basically 10% improvement potentially. So then is there given how much, big data costs to generate, collect, and run, is it worth that cost? And they sort of point out too that there's still a role for small data in the era of big data. Okay, so this talks about big data, but the other thing you might hear about is data science. So this comes from a website of a data scientist. They talk about domains you sort of need to know about, and again, and the overlaps, right? So there's three sort of major domains you sort of need to sort of be aware of or familiar with. Hacking skills is basically, being able to program, and use sort of programming techniques well. Math and stats knowledge, that's obviously the domain that sort of I represent. And then this last one, again, this gets called many things. Again, I think informaticians talk a lot about use cases. I think if we're, as researchers, we sort of have, the other thing term right here is data domain expertise or subset expertise, but that's basically knowing about the problem you're working on. So again, many of you in the room are probably coming from the health services domain area, but again, with big data, there's lots of domains. As Beth pointed out, I've worked a fair bit in genetics and genomics. That'd be another area, another data domain. There are people that work with neuroscience, scientific data, things like imaging or electrophysiological measurements. That's another domain. So there are lots of different domains. So anyhow, those are the various areas of data science. And again, the overlaps are sort of, so if you have that magical 3 in the middle, you're the data scientist, okay? So this is, again, I think, data science is a very generic term. I think how people define it is highly variable. What I like about this picture, though, is it sort of says the 3 things you need to sort of be able to start to do it. And they do point out that potentially, much of my, I guess selfishly, that if you're doing this without statistics, you're in what they call the danger zone. That's not a good thing to be in. So anyhow, so these are various things. And again, I'll talk mostly about stuff, I guess, here. So again, most of the examples I'll have for methods are here, and I'm happy to talk with any of you guys with the subject expertise to figure out if there are ways I can sort of apply these methods to the problems you guys are working on. Okay, so now starting about this idea of data science. You saw machine learning, right? You saw that as being one of the things people sort of need to do. That to be sort of one of the big things you need for data science. That being said, right, so the machine learning represents a class of algorithms where the goal is to make a prediction. So here's what I'll tell you though. How many of you are familiar with regression models? So regression models is basically the starting point of machine learning, which means you guys are all machine learning people without even knowing it. So basically, regression is sort of like, sort of the thing on which they start, especially linear regression. Obviously, linear regression makes assumptions about your parameters and your data and your model and your outcome. If you want to start to be nonlinear, that's sort of where a lot of the work in machine learning sort of focuses on, is thinking about more flexible nonlinear approaches. The other thing they're focusing on a lot more these days is with this petabytes, zettabytes of data, if I even want to fit a basic linear regression model, that's actually not easy. So how to come up with new computational algorithms to do that as well. So again, this sort of, so again, a lot of what we talk about in statistics is inference. So you're probably familiar with things like p-values, confidence intervals, t-tests, chi-square tests. A lot of that is about doing inference, right? With machine learning, the focus is a lot on prediction and making predictions. So then the question sort of then becomes, and again, sort of like if you think about the role of statistics of data science, is where you divide things between inference and prediction. So I'll give you a couple sort of two countervailing viewpoints. One is from this guy, Jeremy Howard at Kaggle. How many of you have heard about Kaggle? I see a few hands. So I'll explain Kaggle. So Kaggle basically is a place that holds these open source data competitions. And basically they put up public data sets. They say, build a predictive model to predict the outcome of interest in this data set. They basically have a competition, and you submit your code in. It's public, and then they have a real-time leaderboard. So basically, you build it on the data set they give you. They have a data set that is their test data that they're going to try your algorithm on. So you send in your algorithm to Kaggle. They try it on their test data set. They report the results, and they basically have a real-time dynamic leaderboard for who's doing well. And they do this for a month or two. At the end, the person with the best predictive model is the winner. So basically open source, big data, machine learning, and sort of this idea of sort of this public competition and winning. Okay, so basically the CEO, Jeremy Howard of Kaggle, basically they asked this question. Everything they do with machine learning, so it's data driven in black box, and they ask, is there a downside to doing this? So basically what this says is I'm going to let the computer figure everything out. I'm not going to use any data knowledge, any domain knowledge. And basically he sort of says, in a long way, that's enough. So his answer is you end up with, some people might argue that you don't end up with a return statement problem, but that's not true. The algorithms, so it's all about the algorithms. It tells you what's important, what's not. You end up with a pretty model that works. There's not much to argue about here. So he's thrown the gauntlet down. So that's one viewpoint. But again, what I would sort of say is all of the data sets they even get, so again, this is that data generation process, they've sampled in a certain way, they've defined a population in a certain way, and if they don't understand that or don't know that, these must be horribly wrong, right? Or they could make bad predictions. So that's sort of the other side. And thinking about sampling, again, population sampling, that's sort of where really statisticians are trained. And again, this is a quote from a book called Doing Data Science. Let's see. So these guys actually take the opposite view. So this is given raw data, constraints in a problem statement, how to navigate through that maze and make the best choices. And then every design choice you make can be formulated as a hypothesis against which you're going to do testing experimentation. So this is actually probably closer to I think the way biostatisticians sort of view is what they're doing. So anyhow. This is more the biostats model for thinking about data science. And again, there's a really neat paper by this late statistician named Leo Feynman. It appeared in Statistical Sciences, where he basically argued. So he's a statistician. He was at Berkeley. He actually argued for prediction relative to inference. It's one of these papers that had him writing the article. They got a bunch of famous statisticians to write responses. So he did prediction, and then he had like 5 or 6 discussants. 2 agree with him, 3 really didn't agree with him. So then he sort of came up with a rejoinder. So it's sort of a really interesting question. I think what I can tell you from my own take is basically this idea of machine learning as a statistical method has really taken off a lot. Sort of in my field, I sort of see a lot of emphasis being given machine learning. What I actually don't see is more the other things I was talking about, which is thinking about issues of sampling, measurement, bias with these big data problems. So anyhow. So coming back to that picture I showed you earlier, and just talking through the steps of that picture. So first is developing an understanding of the application domain and relevant prior knowledge. So this I think most of you guys come to already because you guys are working on a particular problem. So you have that, and then thinking about the knowledge of KDB processing customer's viewpoint. This is quotes from that paper by Fayad et al. So these are people that work at companies, so they think about the data knowledge being given to customers. Second, you're creating a target data set. And again, to me, step number 2 is a huge one, right? Because step number 2 basically says, what am I defining as my target population? How do I want to collect data on them? And then potentially, if I'm doing things like merging data sets, are there biases? Are there biases or issues with trying to merge multiple data sets on these people? And then the third step is the one I told you. This is the one that, probably takes, again, data scientists would say that step number 3 relative to the fancy stuff is most of your time. So 89% of your time is spent on step 3, which is data cleaning and processing. And again, basic operations, removing noise if appropriate, collecting necessary information, model account for noise, and then if you have missing data, which is a huge one, how do you handle missing data, and then thinking about time sequence information and changes. So again, the time sequence information known changes is kind of one thing we talked. So with the Google thing, right? So what I said was before 2011, they had certain search terms. After 2011, they didn't. So if you know that ahead of time, you can start to think about how to adjust for that here before you even fit your model. But again, it requires sort of knowing that, which again, Google didn't make it kind of completely transparent. Okay, so 4th step is data reduction and projection, and then 5th is so the 5th and 6th steps are basically the stats part. So one is thinking about data mining or machine learning tools. Another one is doing exploratory analysis. Yeah, sorry. So picking those out. So 5, 6, 7 are doing that. 8th is actually interpreting the patterns, and then 9th is actually acting on what you find. But again, things to note here is it's actually, I showed it to you as like an ordered sequence of events. It's not. It's really iterative. So it might be when you do this, you find patterns, and that pattern suggests that you probably are biasing your answer towards a certain kind of data point, and you might have to go back and want to reprocess the data, trying to downweight that or something. So there's a lot of iteration here as well. So anyhow, that's sort of so KDD, just to remind people, stands for knowledge discovery in databases. So I think when you think about the big data problem, I think really that KDD paradigm is sort of the one that's really a useful one. And again, the way the authors write that paper, it's super abstract, right? So I think what you have to do is take that paradigm, figure out how does the knowledge you have in your data domain sort of inform or influence that process. Okay, so the kind of tasks that arise in data science. So like I said, if you guys all know one of the big tasks in data science is just basically fitting regression models. And again, I think one of the big challenges going forward of thinking about big data is basically you're going to be fitting regression models to data sets where you have potentially like 1 trillion observations. So that becomes a computational one. And again, basically, sort of in basic statistics, if you fit linear regression, one of the key things you have to be able to do is invert a matrix. So if your matrix is super, 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 super huge, it becomes really hard to do that. So that's really one of the big data challenges. Even basic things like fitting regression models, like how do you make that computationally scalable and feasible on really big data sets. The other things, we'll sort of go through high-level discussions of these, which are basically these machine learning methods. And again, yeah, so one thing machine learning people do is basically sort of break down their, so I described 4 sort of major tasks that people do in machine learning. So one is, I'll go through these in more detail. One is called supervised learning, where you're using information to predict an outcome. And again, you can do that with a linear regression model. You fit a linear regression model, you have y equals your linear model. You put in, once you have your regression coefficients, you can use that to come up with a y hat. Y hat is your prediction, right? So again, you guys have probably all done one case at least of supervised learning. So that's supervised, so the idea there is you have a dependent variable that you want to predict. The other one is actually something that's probably less familiar, which is unsupervised learning, which basically says you don't have the dependent variable, but I want to figure out are there subgroups in my data set. And that gets called unsupervised learning by machine learning people. In statistics, we call it clustering. Can we figure out a way to identify subgroups of people? But again, in my mind, if you think about that KDD process, finding subgroups of people is really important if you're going to behave differently towards the different subgroups, right? If you're still going to be, so I think about cancer, again, which I'm really familiar with. So there, using genetic data, they figured out ways of, at least in breast cancer, of finding subgroups of breast cancer that you're going to treat differently. So some subgroups of breast cancer, you're basically going to give sort of more aggressive chemotherapy and radiation therapy treatments to. Some you're not. So potentially this information has helped figure out who not to give that treatment to, right? And then sort of figure out how to tailor the treatment better. But if you're planning to on to give everyone the same treatment no matter what, and not to change the treatment protocol, it makes no sense to be doing this unsupervised learning with that data. Number 3 is called a recommendation system or recommender system. And again, you guys are probably see this a lot in practice. So if you ever bought anything on Amazon, like I have, based on your purchase history at Amazon, you might see the things. People who bought the book that you just did also bought book 1, 2, 3, 4, 5, 6. So that is a recommender system. So those get used quite a bit as well. And the last one is something I'm calling sort of anomaly detection. And the idea basically there is you might have a process, right, for monitoring something. And actually, so you might have like hospitals might monitor. You might monitor sort of how they're doing on various kinds of outcomes, right? So then with those hospitals, you might see hospitals that are performing way better than everybody else or way worse than everybody else, right? So so in the machine learning community, they would call that, those would be the anomalies. But again, anomaly makes sound like it's a bad thing. It just means that it's different from the norm. It could be like overperforming as well, right? So there's really no, it's just, it's different from the rest, basically. Okay, so supervised. So I'll just give you a little bit of background on these methods. So supervised learning. So the goal here is you have a training data set with X's and Y's. So X's are your independent variables, Y's are your dependent variables. You build a model. And again, then you take a new X that wasn't in your data set and you predict a Y for that data point. And again, if you all have fit linear regression models, you can do that with linear regression. And again, this is a lot of what's being done now. And some examples. There are public challenges available to basically do this. Where they put a data set online, they then say, find me your best predictive model on that data set. So I talked about Kaggle earlier. So here's another one by Dream. Have any people heard about Dream? So again, Dream stands for Designing Reverse Engineering Assessment of Methods. And what I can tell you actually is one of the people involved with the Dream project is actually faculty on this campus. His name is Jim Costello. He's a faculty member in pharmacology, so he works quite a bit with these Dream challenges. Again, he comes much more from the genomics data domain. But again, even with Dream now, they're trying to look at, a lot of what they've looked at has been in the cancer area. So now the one they have going on right now is, I think, looking at mammograms for breast cancer imaging and trying to see if people can come up with and the idea here again is basically, can we basically crowdsource a solution for building a good predictive model? So they put this data, make it available to the community, and then basically use use that data to then see what the community comes up with as sort of the best model. And one of the things they sort of find is really interesting is we can come up with a model, Harvard can come up with a model, Duke can come up with a model, but if those guys at Dream take all the predictions from Colorado, Harvard, and Duke and combine them, they actually do better than any of us individually. So that's one of the things that they found quite a bit. It's basically by taking sort of every group's little model and then combine them. And again, there's sort of, so again, basically in the machine learning community, they would call that aggregating learners or stacking learners. They basically find that they do better than any of the individual groups. Okay, so those are supervised learning. So again, supervised learning regression is sort of the standard case that people use, but there are actually lots of other methods out there. So I've just listed them here. And again, if you want to sound like a data scientist, you just name drop these at your cocktail parties. So you have support vector machine or kernel machine methods, random forests or ensemble methods, k-nearest neighbors, as well as tree methods. These are things here. These are methods. And basically, the way they're fancier relative to linear regression is they basically relax the assumption of linearity. So if you think your effects are nonlinear in your data set, you might think about fancier methods. If you think linear is good enough, you could probably get away with linear regression. Yes?
So how are people incentivized to share their work here? Or is this just happening in an altruistic manner?
So the public challenge, yeah, that's a great question. So with that one, what I know about the dream for sure. So okay, right. So with capital incentive, it's there's a money prize. With the dream, there's not a money prize. What they've been able to do fairly successfully. So I will say the dream also involves folks at IBM. And IBM, they have you've probably heard of Watson. So you probably hear a lot about Watson, the chess or Jeopardy playing computer. Watson's also doing health data stuff. So there's sort of a group of health data scientists at IBM that work with the dream. They're part of the dream team, and basically they've been able fairly successfully to get these publications sort of into high-profile publications. They've been doing a lot of genetics and genomic stuff, so they've ended up primarily in, there's a journal called Nature Biotechnology, which some of you might be familiar with, that these papers published there. What ends up happening though is basically every participant is listed as a co-author. So it's basically, you know, when you see the actual author list, it's maybe a few people, and then everybody else gets into the DREAM consortium. So that's sort of been the incentive structure so far, but I think that's a great point. I think data sharing here is challenging. I will say with the, I mentioned earlier about data privacy, with this breast cancer one, they're actually having problems releasing the data because having the breast cancer data out and then potentially being able to overlay with other data sets, they found that there was a high risk of disclosing the women who contributed data sets. So to me, data sharing is a good thing, but again, I mean, this idea of the privacy, I've said it a lot, but I'll say it again. I think the privacy one is actually going to be the big challenge going forward. It's thinking through how to maintain sort of privacy in this. But that's a great question about the incentives. So here's one key assumption, though, I will say, which is when you sort of build these models, supervised learning is great, there are lots of algorithms, but you always assume that your test observation actually comes from the same distribution as your training data set. And again, I told you in that Google example, they sort of changed the distribution of things after July 2011. So there was actually a shift where basically the distributions changed after that point. So that would be an example of where basically your supervised learning wouldn't work as well, right? Because if you have a structural shift in some way in the data, then this idea that the test data and the training data, and again, the training data is what the people build their models on. The test data are sort of what they don't get to see and what Kaggle and Dream used to evaluate these methods. So the idea is by holding the training data back, you get an unbiased evaluation of predictive performance. But if the you know, and again, you can imagine this being done in lots of ways. I mean, you know, sort of taking it back a little bit with in epidemiology, a lot of data sets that get collected in epidemiology are what are called case control designs, where basically you have some people with disease, some people without disease. Okay. So by definition, in your data set, you're going to have way more cases than you would have in the general population, right? So if you build a predictive model based on your case control data set, and then try to use that to predict, you know, what's going to happen in the population, you're going to have a problem because basically the population distribution is different than your case control distribution. So that's a very basic example. But again, I think that people think, again, coming back to what I said earlier, in that KDB pipeline, how you select your data is really important. And again, coming back to reproducibility, if that step is not documented, that's actually, you know, that can pose problems very quickly. Right? So again, I think about, I think when I think about reporting how you select your data, you know, there are people in the audience that work on things like meta-analysis. So in meta-analysis, you have sort of this Prisma statement for like basically what's the pipeline and diagram for how you do the meta-analysis. So you have to list off, you know, you do a PubMed search or Cochrane database search and what terms you search on. You have to list all those things out. You basically need some kind of protocol like that when you actually. This is just for generating the big data question. Because if you don't, we're going to get to, you know, you're basically going to be, the idea of reproducibility, replicability is going to, you know, not be available to you. So that was supervised learning. Unsupervised learning, again, we have no Y variable basically for unsupervised. So what you want to then do is basically you want to find a subgroup of subjects based on the X's. And again, the idea is, it really is sort of helpful if the idea is you want to treat subgroups differently. So again, just for dropping some terms here, There are lots of machine learning tools that do clustering or unsupervised learning. So here's some listed here: spectral clustering, manifold clustering, k-means, mixture models, hierarchical supervised decomposition. The nice thing about clustering is you get nice, like pretty pictures. So this is actually just simulated data. I actually got this from a website called Stack Overflow. So I will say Stack Overflow is a very great website for machine learning questions. If you have questions about machine learning or even statistics or data science, I think the Stack Overflow has a great resource for that. So basically, I had a bunch of data points, and then I have DC1 and DC2, which are two variables. And I basically want to cluster them into three groups. So I've color-coded how, so I haven't told you what cluster algorithm run, but basically, let's say I run a cluster algorithm. It assigns all these observations to be in group 1, all these to be in group 2, and all these to be in group 3. So things to note here is that the group 1 is really separate from the other two, whereas there's a little bit more of a, the 2 and 3 are less separated. The thing about 2 and 3, though, is 2 tends to have higher values on the x-axis, right, relative to group 2. And then they're a lot more comparable on the y-axis, or similar. Okay, so I didn't tell you how to, what algorithm I use, but basically the thing you should just keep in mind with unsupervised stuff, one big challenge and issue with these algorithms is you have to figure out how many groups are in your data set. And it's kind of a really hard problem, right? Basically, I could say there's just one. So if I just look at the picture, I might actually say there's two groups in my data set, right? Because basically there's this big white space right here, and I'd probably say over here is one group, over here's another group. Somehow, and the way I haven't told you, basically, I've actually said there's not just two groups, there's actually three groups. And here's how I get three groups. But the question of how, so again, it's sort of a hard problem, right? Because you don't have a y variable. You're basically basing it on your x variables, and the idea of how many clusters there are is a challenging one. The other reason is basically because some algorithms require you to input the number of clusters when you run the algorithm, and some don't. So the other sort of issue is when you have this kind of data, how do you define the distance between observations, which is sort of fun. Basically, all these methods sort of define distances in different ways, and the question becomes, which is the right distance you want to be using for your data set? And again, there are lots of algorithms out there, but again, I would sort of say these basic issues of data handling, data sampling, to me, they're actually the more problematic ones, especially if you don't know how they were sampled, right? And what you want to be making inference about. Okay, recommendation engines. These are, like I said, ubiquitous. Given your purchases, you get recommended things based on customers who made similar purchases. And the concept is, given your purchase history, they want to identify similar customers and recommend their purchases that you have not made. And again, if you want terminology here, for recommendation engines or recommendation systems, there are two kinds of algorithms. One's called collaborative filtering, and the other's called content-based filtering. And again, sort of the nice thing about recommender systems is they basically sort of, a lot of them get phrased in this way, right? So you are the users, that's all of us. V are the items. Let's say these are television shows on Netflix that we like watching. So if I'm person U, I watch this TV show, and then I find out who else has watched this TV show. And let's just call it, for concreteness, let's call it Mozart in the Jungle, okay? So you see Mozart in the Jungle, who else watches Mozart in the Jungle? This person does, and this person does, right? So then you want to recommend, then this person's also not just watched this show, but also watched this show. And let's say that TV show is Fleabag, okay? So you might get recommended Fleabag based on the fact that this person watched the same show as you and has watched Fleabag. Down here, let's say the show is, we'll keep it more mainstream, Orange is the New Black. And then because this person watched Mozart in the Jungle, Orange is the New Black, you recommend Orange is the New Black. That's kind of the way this works. So basically you have this graph, and again, the main thing here then becomes like just querying what else everybody else has seen who's seen the same show as you, right? So this is 5 users and 4 TV shows. We know Netflix has more than 5 users and more than 4 TV shows, right? So if we're talking, millions of TV shows and millions of users, the idea of querying becomes a lot more computation intensive. That's probably why it's really slow when you click on the website. When you click on the TV button. Anyhow. Okay. So again, with recommendation engines, there are issues, and the main one I brought up, which is basically in that graph, the number of points on both sides goes up. It's actually super huge. So the idea of just querying that database is actually intensive. There are other issues, which is overfitting, sparseness, measurement error, missing data, and then again, sort of just reiterating computational cost is actually just the big one. Just to remind you, Netflix is one of those FANG companies. So they have like people in their group that are doing machine learning with recommender systems that have access to like lots of servers and lots of computation to be able to do this sort of in a pretty fast way. Okay, so I'm looking at the time. I have 15 minutes. You see I have 40 slides. I'm not going to cover 40 slides. I'm going to probably just talk a little bit about, so this is the second half of the talk, which took, first half took a lot more than I have time. But anyhow, this is just talking about sort of my own research. And again, a lot of what I look at is thinking about machine learning for doing causal inference modeling. And just to give you a background so everyone can get on the same page here. So I'll talk a little bit about causal inference. I'll talk about one of the things I worked on, and then I think that'll be time.
Debashis.
Yes.
So I was going to do sort of an overview of the day from 9:30 to 9:25. So you can, if you need a little bit more time, I don't need 15 minutes to do the overview. So. Yeah,
but I'm not. Yeah, we'll just see how this goes. I mean, again, I think the first few slides are sort of meant to be more introductory, and then the last bit will be a little bit of research. So basically, again, there's a lot of interest in statistics and other disciplines on using causal inference methods. And the idea here is you want to understand the effect of a treatment. In clinical trials, you typically look at the effect of treatment by randomizing people to get the treatment or not to get the treatment, and then looking at the outcome. In most settings, you can't randomize treatment for lots of reasons. So a strategy that was used, proposed over 30 years ago by Rosa von Rubin is used in this problem called propensity scores. And again, the idea here is that the propensity score is the probability of receiving treatment given covariates. And then conditional on that score, you get what's called covariate balance. So the basic idea here is like, when I do a clinical trial, I flip a coin, right? Heads, you get treatment, tails, you don't. You can think of this as basically, I'm now going to make a much fancier coin. The coin, the chance of it coming heads or tails depends on your covariate values. That's really the basic idea here. And this is just some notation. So if we have T being the treatment, let's keep it simple and have it be binary. What potential outcomes does is the following. You have to be able to imagine your outcome given you get the treatment and your outcome given you don't get the treatment, you get control. So you actually have a random distribution for that as well. And again, the big problem is going to be in practice. This is what I write down as possible. I only observe one, right? So for every person, I'm only observing one of these. If they get the treatment, I observe Y1. If they get the control, I observe Y0. And then based on that, I then can define these causal effect estimands, and this is the one that people use a lot. ACE stands for average causal effect. And again, for this whole thing to fly, you sort of need this assumption. And what this basically says is I've collected so much covariate information as I can think of. I can basically think of T, which is the treatment you actually do receive, and these potential outcomes as being independent. So that has a fancy name in statistics. We'll just abbreviate it as SITA. And the propensity score basically is what I define up here. So this is the probability you get the treatment given your covariates. And then with SITA, you have this implication that, so before I had X, I had that conditional independence given X. Now I have it conditional on E of X. This is one number. Before this was X could be really, really, really big. And in the big data world, yeah, we would be thinking like hundreds of thousands, thousands or hundreds of thousands or something. So I've gone from hundreds of thousands down to one number, which sounds really appealing. So a lot of what's been done in this literature is to basically estimate the propensity score and then use it in a way to estimate causal effects. So these were the questions I had planned to address for today. They will not both be addressed, but I'll give you a flavor of some of these things. So in these problems, one of the things I've been really interested in is thinking about how you formulate and write down models and pick variables. And basically, well, the question I'm asking is, well, it says here, why is that different for causal inference problems? And when I say different, it's different from standard approaches. And then the other thing, which is, think about how can you fuse machine learning with causal inference. So I'm not the only person that worked on this. This is a book by Mark Vanderland and Sherry Rose. Mark Vanderland's a faculty member at Berkeley. Sherry Rose is now at Harvard. It's called Targeted Learning. Came out in 2011. It looks skinny because this is a slide. It's 600 pages. So I'm of the generation where I still need the paper copy to read it, but you can download it for free as a PDF. So it's out there. So they basically have one so basically this is one general framework for handling basically in principle any inference problem. Sounds good. I would tell you the devils are in the details, and sometimes it's sort of hard to flesh those out from the book. So I'll say a little bit here about sort of the way I think about models and variable selection here. So basically, I would say the reason these things are different is basically because we actually have two models to worry about. One is something I call the outcome model, which is what defines the causal effect. The second was propensity score. So the thing about propensity score is the propensity score involves treatment and covariates. It does not involve the Y. Okay. So because it involves the Y, it sort of it has no role with the Y. So the outcome model defines your scientific estimate. And the propensity score model, the main things here are we don't really want to interpret the model. We need, let's say, probabilities. And we also want to, in principle, be thinking about having this balance in your covariates. So here's some examples of the outcome model. So that I mentioned that ACE model earlier. It corresponds to this kind of a regression. So it takes a difference of y1 and y0, and it basically says it's equal to a parameter tau and then a noise term. So this is a little bit like linear regression, right? This is my dependent variable. I have one regression coefficient and I have a noise variable. So that's what ACE estimates. So the other thing to point out here is if I were to, so here I have no other covariates, right? So down here I actually have covariates. So what this one says in this model is that the difference in outcomes depends on your X. So another way to think about this is that these variables are basically defining interactions. Okay. So up here I have no interactions, down here I have interactions. So basically what that means is if I want to interpret tau, it's actually going to be the average causal effect for the entire population. That's not the assumption of tau, that's not the interpretation of tau star. Tau star is going to be the average causal effect when basically all these X variables are zeroed out. So basically the regression parameters, and again, this might look more complicated because I have initial outcomes, but we teach you this in linear regression classes, that if I have a model with just age in it and a model with age and gender in it, the interpretation of age changes. And that's all I'm saying here. But this model is only telling you about what's the causal effect you want to estimate. Propensity score. With propensity score, this is just the key cartoon that I use quite a bit. So this is like a one-dimensional case, which is easy to plot. So I can imagine basically this being sort of so the propensity score is a probability, so it's between 0 and 1, but let me say I transform it so I can make it be a real number. This is looking at the distribution of the transformed propensities in the control, and that's that histogram. This blue one is the distribution of transformed propensities in the treatment population. Okay, so the thing you note is that for causal inference, what part of the picture matters the most? I'm going to make this easy. I'm going to give you three choices. The left, the right, or the middle?
Yeah.
The middle. So the middle, and again, so basically we want places where we have treated people, we want places where we have controlled people. That happens in the middle, okay? So over here, I have people that are on control, and I have nobody that has treatment. Over here, I have people that have treatment, I have nobody that has control. This whole causal inference paradigm is based on, for every person who gets the treatment, I need to find at least one person that's comparable that has control. So the point being that there are no comparable treated people over here. There are no comparable treated people over here. The only place where I have comparable treated controls is in the middle. So causal inference is all about the middle of this picture, okay? And that's identical to the idea of, so basically where you have it in the middle is basically effectively where you have this covariate balance happening. Over to the left or to the right, you have covariate imbalance. And the upshot then basically means that if I use these observations in a causal analysis, I'm relying basically on my modeling to sort of synthetically come up with treated and controls that are comparable. And one of the big things about causal inference is they really want to avoid things really based on a model, right? Because the other issue here with causal inference is you basically have you have these unidentifiability problems and stuff like that. So the point here of all of this was basically that these two models actually have different goals. One is you want so the propensity score goal, the goal really is you want to get this balance between treated and control. You also want to figure out which observations have comparable people from the other group. So if the middle is really what you care about, this is actually the opposite of what machine learning does. What the machine learning wants to try and do is take this picture and push those two groups as far apart as possible. Okay? Because the goal of machine learning is very much about separation, whereas we actually don't want separation. We want unseparation for causal inference. So basically, what that means is, really, if we want to do causal inference sort of in a sort of a robust way, we actually have to think about a different criteria for how we optimize the optimization. So we can't use sort of standard machine learning optimization criteria. We need other ones, and here are just a couple papers that look at other ways of doing this. Okay. Trying to think what else. Yeah. So it's still fairly high level stuff. So the other question I mentioned too is what variables do we want to include in a propensity score model? So there's lots of advice in the literature. It's not quite clear what the right answer is there. And I've just given some examples here. And I would say too, like what I presented to you was called the potential outcomes. That's actually something that Ruben has sort of developed quite a bit. There's other ways to think about causality, and another one is by this guy Pearl, and he's a computer scientist. So he sort of formulates this all in terms of graphs, where he thinks about identifying separation in these graphs as a way of inferring causality. Let's see. Yeah, another sort of useful picture. So when I do these causal inference problems, I actually find this to be another sort of useful diagram. So this is sort of your data, okay? And this is not a big data matrix. It's just a small data matrix to fit the page. But the thing here is you basically see my columns. So basically what I have in the columns are the potential outcomes for the first two, and then I have the treatment they actually received, and then covariates. So I'm making a very simplifying assumption here, which is I basically have no missing values in the x variables, okay. So you see missing values, they're represented as question marks. So the way to think about this is person 1 received t equals 1, their potential outcome, we didn't get to observe, and that's y1. We didn't observe y0, right? Person 2, t was 0, so we observed their y0, that's y2, we didn't observe y1. Okay? So again, the idea here is basically every row, right, I want to have one question mark, because I'm missing one potential outcome for each person. The other thing is I told you this, I'm assuming my treatment is binary. In reality, you can imagine much more complex treatments. But again, much more complex treatments basically means I'm going to have more potential outcomes, and I'm going to have a lot more question marks. Okay. So that's sort of the setup. But actually, by sort of writing it down this way, you sort of get to this very simple idea, which is with the missingness data mechanism and this assumption, it actually is equivalent to saying that you can think of the question marks. So you can think of that as time distribution. You can think of that distribution as being effectively missing at random. So what you can then do is basically the following, which is you fill in your missing data, and people that work in statistics, they call that imputation. Once you get that, once you fill in the missing data, you have a complete data set, and then you can sort of do your procedures on the complete data set. So that's sort of one of the things we've looked at quite a bit. Yeah, so it's sort of a good high level. So basically, things to note here. So if you think about variable selection for causal inference, you have y0, y1. So you actually have a two-dimensional y. So that's why it's multivariate. So the approach in this paper that we published a couple years ago was to impute these special outcomes and then take the difference and then run a lasso. So a lasso is a very common algorithm for machine learning. Stands for least absolute selection and shrinkage operator. And this idea is based on the application of what's called a predictive lasso. So again, I told you there's been a lot of work on machine learning and statistics. I would say the lasso paper, which first appeared in by Tipshirani, I think it has like well over 30,000 citations from 1996, which is, again, that's an anomaly for stats papers, citations. Yeah, so again, things we figured out there was, excuse me, when you impute data, you can do what's called single imputation or multiple imputation, and we basically found the multiple imputation approach to work better, which I think was the best. But how you impute the data is also really kind of critical. Let's see. I think the last few things, so there's a lot I'm skipping. Let's just go to, yeah. So this is also pretty neat stuff. So this actually sort of, this is a new machine learning algorithm for doing causal inference. So I've written this equation before. This is the assumption, which also gets called no unmeasured confounders. And it's based on conditional dependence. If we want to estimate the average causal effect, you can actually relax that assumption. So it's a one equation or two equations. And it turns out, excuse me, you can link up this idea to dimension reduction methodology, which is again, another thing that's been worked on a lot in statistics. There's a lot of equations with that, but I'll just tell you the idea is you have subspaces that capture this conditional independence, and you just want to like identify the basis of the subspaces. So these two objects that people study quite a bit called central subspace and nonlinear subspace, and we use CMS. There's a lot of equations here, but things to note is down here. So this is the average causal effect that we care about. It turns out if we model y1 and y0 from the observed data, we can find this subspace basically. And it turns out that if we, under a couple other assumptions, the observed data gives you the exact subspace that the potential one does. Yeah.
Is this getting around the unmeasured confounder problem?
No.
Okay.
No. It assumes it. It exploits it. This way. In fact, so basically it sort of gets so there's an algorithm up here, which is basically you estimate these things for the two groups separately. You regress your outcome on these covariates, and then you estimate a regression causal effect. But actually, one of the nice things about this, so Diane asked about, it doesn't get rid of no unmeasured confounding. It does actually relax this covariate overlap assumption. So that's kind of a neat thing that we sort of found in the process. And again, Jamie Robbins is a person who's worked quite a bit in this field for a really long time. He has an algorithm that's called G computation. You can think of this as a semi-parametric version of that G computation algorithm. The other thing that's sort of interesting, so let's go a little bit here towards the end here. Sorry, I can't read these, but so our proposed method is actually to the right. And one of the things that's kind of, so TMLE, right? So that was the one that from that 600-page book. So we compared it with a 600-page book. One of the things we found, you can't read these, but the parentheses are standard errors. And one of the things we actually found was so TMLE is supposed to be, in the sense, the statistically most optimal thing to be doing. So it should have the smallest number in the parentheses. Ours are a lot smaller. And it turns out they're a lot smaller because basically this assumption we make was dimension reduction. It basically, at least this condition called super efficiency, which is super theoretical and not something we're expecting. So one thing we're trying to do now is basically use our CMS thing as a first step, combined with targeted learning at the second step. So we're hoping that that'll sort of get around that. But there's a lot more flexibility potentially with this modeling than some of these other models have for the appeal. So wrapping up, so this is one thing that this is a quote from Gary King, who was an author on that paper, Laser et al. From Science. Big data is not about the data; it's about the algorithms. And again, from my point of view, there's a lot of interest in machine learning. It's great, but I think you think about analytics, there's actually going to be a causal piece to it that's really important as well that we'll sort of need to address and think about. And to me, this to be a sort of the future of statistics. So this is a picture from, so this is a paper by some folks at Google, and they basically talk about, they're the statisticians, right? So they're at the bottom. They basically talk about how they get the data. The data does not live in one place. It lives on a lot of servers. So what they have to do is basically, from server logs, they then do this use this MapReduce framework, which is a very common big data management framework for querying and getting the data. So in my mind, so the reason I call this future statistics is the following. We always assume basically in our models that data lived on one server, okay? So all the stats courses you've taken, stats talks you've been to, assume a one server kind of model. We actually now have a K-server model, and my prediction is that this will have major ramifications for how we think about statistics, because you have to now start to worry about data being on different places. If there are biases across the servers, you have to account for that in your inference. These queries take a long time. In stats theory, we've just said, oh, just collect more and more data and more data and let n go to infinity, right? So now we actually have a constraint that we've never thought about in terms of inference and how you manage that. And then sort of these phases of map and reduce, how you actually account for those as well in inference. So I think actually it's not going to happen probably in my lifetime, but I think the way we think about inference as statisticians is going to change because of big data. But coming back, that was the stats part. There's also just big data scientific things to think about. So we have, and I've said this a few times now, the ethical privacy issues of big data are going to be a big one, and how we navigate that space remains to be seen. Cost-benefit analysis. If simple gets you really a lot of the way, really you have to think about is how much bang you get for your buck with collecting big data and doing big data analysis. And again, from my point of view, thinking about biases and designing studies of big data is sort of going to be also a very open topic for the future. So with that, these are the papers. So I talked a little bit about the first one and the third one. I didn't talk at all about the second one. But a plug. So I'm teaching a new class in the spring. It's called Causal Analytics for Public Health. It's going to be a more introductory version of machine learning algorithms as well as causal inference ideas. So if you're interested, please let me know. Thank you.
Thank you.